In this video, we'll discuss how do we generate new functions from some elementary functions, old functions. This is the section 1.3 in book. So this is our section 1.3. So by the end of this video, I hope you will be able to understand some way to generate new functions from some given known functions, right? So let's start from the function we know. So give a notation for that. So let f here be a function from D. D is the domain of F, right? From D to R, right? Codomain is the set of all real numbers. And equivalently, we have a short notation is F, comma, D to R. As this F, D, right arrow R is a representation, means F is a function from D to R, right? Let's start from easy way to generate shifting, right? We fix C here be positive, fix C be a constant, C is positive. We can define new functions, right? For example, we can define y equal to f of x plus c, right? So that is a new function. You can see that the function value plus c here. If you try to make a connection between the original graph and its new function, f of x plus c, right? Suppose the green one is our function, the graph of this function y equal to f of x. You can imagine that if you plot c in the y coordinates, then the function is basically shifting up by c. So this is y equal to f of x plus c, right? And in the same idea, you can see if you have a new function, y equal to f of x minus c here, then the graph of the new function will be obtained by shifting the original one, and down by c unit, right? This will be y equal to f of x minus c, because whenever you get x value, put it in your new function, the function value is the original one minus c, right? Or you can, this is called vertical shifting. You shift up or down. So this is called, this tool here is basically vertical shifting. We can also do the horizontal shifting by plus or minus c on x, right? Another function, y equal to f of x minus plus c, right? In this case, if you want to get the graph of this function, you have to shift the original one to the left, right? Let me use the black one to represent this function here. So this is y equal to f of x plus c, right? And also you can minus c in the x coordinate, x of x minus c. In this case, you are shifting to the right side. So the graph of this function will be y equal to f of x minus c, right? So this is basically how do we get the new functions by shifting, right? So this pair is called horizontal shifting. Here are other ways, right? And let's try to understand a few other ways. The ways we'll be using in multiple situations. Now let's start from two functions, right? So let f g here be functions from what? From D to R, right? And also let C here be a constant, be a number, be a constant, right? We can generate new functions by multiply the function by a number. For example, C times F, right? That's a function, right? What's the C times F do is if you take any x inside from our domain, C times F of x is basically C times F of x, right? So that's what does our first new function does, just multiply the function value by C. And also you can multiply by two functions together, right? F dot g, right? What does this new function do is whenever you have an x in the domain, and what you get, put it into this new function, what you get is f of x dot g of x. Similarly, you can define the subtraction, addition, and also quotient, right? So f plus g, right? What does this new function do is whenever you have x in the domain, put it into this new function, you get f of x plus g of x, right? And similar for subtraction, if you have f minus g, right? To understand a function, all you need to understand is what does this function do, right? What's the rule to assign a value to the to any number in the domain, right? So in this case, f minus g of x is f of x minus g of x. And the last one we will use is f quotient, right? And f over g, then f over g of x is f of x over g of x. In this case, for sure, we need to assume the denominator cannot be 0. You can get this quotient function. Otherwise, this quotient function is undefined, right? So this is how do we obtain new function through multiplication or division or addition, subtraction, or multiply by numbers. And there's one more way here. Let's see the other way, right? And so let fg to be two functions again here. Let g here be functions. Here we don't want to put a restriction on the domain. All we need to require is we want to know that the range of f, right? Range of f is basically the collection of the function values, right? F of x, x inside the domain of f, right? So we want to assume that the range of f is a subset of the domain of G, right? So whenever you have something in the domain of F, you put it into F, you get a function value, which is f of x, right? Then f of x is in the domain of G, right? Being a subset of G. If you try to visualize it, so suppose this is the domain of F, right? And the middle part is the domain of G, right? Inside, you have the range of F, right? Now imagine you take an X from the domain of F. The function, what does the function do is function f does is a function f map at max x into its range, right? This point is basically f of x. So this is f of x, right? And because f of x is in the domain of G, now you can apply this function g here to this number, apply function g here, right? You get a number in the range of G. Range of G. So this number will be represented by G of f of x, right? I can see that if this happens, you get a new function from the domain of f to the range of G, right? That's a typo there. So range of G here. So this is called the composition of these two functions, G, f and G. So the requirement is the range of G has to be a subset of the domain of the range of f has to be a subset of the domain of G, right? Otherwise, this function is undefined. If you get something outside the domain of G, then G of that number is undefined. So we give a new name for this function, which is called composition, right? So this composition, we have notation for that. Go from here to here. It's called the composition of f and G. So the notation for that is G circle F, right? So that's the composition of F and G. So this is called the composition of f and g, right? First apply f, then apply g. You can see that the order matters in this case. If you have different order, you have different compositions, right? So the formula for this function here is if you put x into this function, remember x has to be in the domain of f, right? This is equal to g of f of x, right? Now let's see example. Try to understand the composition of two functions. So let's see that. Okay, so our example here is given two functions, right? The first function, example, the first one is f of x equal to fourth root 8 minus x cube, right? And g of x is another function, which is square root x squared minus 1. So what we want to do here is we want to find f, circle f, or you can compose two same function together. F composed with g, g composed with f, and g composed with g. Right? You can do that. Right? Let's try to do that. So to define this function f composed with f, all you need to do is take a value coming from the domain of f and try to evaluate that, right? By our definition, this is f of x, right? That's basically our definition here. How do we take a composition of two functions? So what is f of x? This is given. So this is f of fourth root of 8 minus x cubed, right? And so this is equal to, now you consider this term as a variable and replace x by that, right? This is a fourth root of 8 minus fourth root 8 minus x cubed, then to the power 3. So that's f composed with f. Now, what is f composed with g? So f composed with g, you put in x. By our definition, again here, right? We don't have any other techniques. The only thing we have is our definition. So this is f of g of x. What is g of x? We know that g of x is square root x squared minus 1, right? And so this is equal to, now we know f is take a fourth root and fourth root of 8 minus the variable to the power 3, right? So this is the variable in this case is a square root x squared minus 1 then to the power 3, right? That's basically what's f composed with g, right? So for the other two, I will leave this as an exercise, and you can finish it by yourself, right? G composed with f, and g circle g here, and this two here, do it exercise. I'll leave them as two exercises. right? So you can finish it by yourself. And now let's see another example. Sometimes we want to get we want to start from a big function looking for possible way to write it as a composition. So that's a very important direction to go. Second, we want after we have a function here, g of x, this equal to third root x over 1 plus x. That's a big function here, right? We want to find f and g such that g here equal to g composed with f, lowercase f, right? Lowercase g, lowercase f, right? We call that, in this case, we call that f is an inner function, is our inner function, and g is the outer function, right? So how do we do that? You start from inside. Look at what's the inner function. What's the function closest to x, right? Clearly, a good choice for our inner function is we choose the inner function f of x equal to x over 1 plus x, right? Now, after you apply this function, what do? You take a third root. So our outer function g of x should be third root of x, right? If this happens, then the composition of g and f, I'm plugging, and let's try to verify that, right? And so this is equal to g of f of x, right? Which is g of x over 1 plus x. So this is third root x over 1 plus x, which equal to g of x, right? So this is basically the two functions which gave you the combination of these two functions gave you this capital G, our function capital G. I hope you have a good understanding of how to generate functions from some old functions by shifting or addition, subtraction, and multiplication, division, or composition, right? There are multiple ways to generate functions.